Hello to everyone. Glad you could make it. Today we are very happy to have Sandipan Kundu from Johns Hopkins University, who is going to tell us about new bounds on chaos and quantum gravity. So Sandipan, take it away.
Thanks, Felipe. I'm very happy to be here, even though virtually. This talk is based on two of my recent papers. I actually never quite understood quantum chaos, so I'm certainly not an expert. So the reason I wrote these two papers were just to explain quantum chaos to myself. The main idea is actually very simple. The goal is to understand certain aspects of quantum chaos, starting from general principles and symmetries. Something what we do in Confound Bootstrap. Chaos is something that we understand intuitively. For example, classical chaos, which is also known as the butterfly effect, is almost everywhere. So that's why we have an intuitive understanding of at least the classical aspects of chaos. A classical system is said to be chaotic if you make a small change in the initial condition, if that leads to a large deviation in the final state, then the system is said to be classically chaotic. A signature of classical chaos is the fact that nearby trajectories in the phase space diverge exponentially fast with time, as shown here. The exponent lambda L is theory dependent, and it's known as the Lyapunov exponent. So classical chaos is something that we have a good understanding of. This is a very nice simulation that I found on YouTube, which demonstrates the butterfly effect quite well. So this is a system of two balls inside a perfectly reflective spherical box. So the two balls, they are basically transparent to each other, and their initial positions are slightly off the vertical axis. In fact, the difference in their initial position is so small that now we cannot even see two balls. We just see one ball, and for first few seconds you'll only see one ball because they're just on top of each other. But then after some point, you'll actually see how the trajectories diverge. So let's start. So this is basically the butterfly effect. This video is actually have a very calming effect. So why not play it again? Okay. So now let's move on to quantum systems. Quantum chaos is actually a lot more subtle, mainly because our intuitive understanding of classical chaos is no longer sufficient for quantum systems. So if we want to have a quantitative understanding of quantum chaos, the first thing that we should figure out is what's the right observable that measures quantum chaos. This is actually a very non-trivial question, and there is no unique answer. But one answer to this question was given long time back by Larkin and Ovchinnikov. In 1969, they argued that thermal out-of-time order correlators are good measure of chaos in quantum systems. So correlators like this. Where rho is the thermal density matrix. And we have two simple Hermitian operators, V and W. Note the time ordering of the correlator. So this is why it's an out of time order correlators, or for short, I'm going to always refer to them as OTOC. More recently, this particular observable has gained a lot of attention thanks to works by Shenker, Stanford, and Kitaev. So this correlator is generally believed to be a good measure of quantum chaos. More physically, what this correlator does, basically, it measures the effect of a small perturbation created by the operator V at t equals to 0 on another operator W at a later time t. So generally for t much larger than beta, where beta is 1 over temperature. However, this is not a perfect observable. So especially in quantum field theory, this observable has singularities, and these are coincident point singularities because some of the operators are sitting on top of each other. So more recently, another closely related observable was proposed by Maldacena, Shenker, and Stanford in their famous paper. It is basically a regularized version of the same out of time order correlator. So as you can see, the density matrix is now distributed throughout the correlator. Qualitatively, this correlator has identical features as the previous one, especially if you wait for a long time. So this is also, because of that, this observable is also considered to be a good measure of quantum chaos. And it has some advantages. For example, the coincident point singularities are not there, mainly because, as you can see from the definition, all the operators, they are shifted in the Euclidean directions by different amounts. Still, this OTOC is a very complicated object, but this regularized version has some very nice mathematical properties that give us some amount of mathematical control. And conceptually, actually, this correlator is of importance importance to high energy theories because this has connection with quantum gravity, as I'll explain later. So for last 5 or 6 years, this quantity has been studied extensively for various systems, and generally it is believed to be a good measure of quantum chaos. Because of time constraint, let me not spend a lot of time explaining why this is a good measure of quantum chaos. If you are interested, you can find them in the original papers or many subsequent papers, talks, reviews. So instead, for the purpose of this talk, let's assume that this is a good measure of quantum chaos so that I can actually discuss the main topics that I'm really interested in. Okay, so in terms of this OTOC, let me make one more point. Throughout the talk, whenever I say OTOC, I'll always mean this thermally regularized OTOC. This is the quantity I'm going to study, that I'm going to discuss in this talk. So in terms of this OTOC, chaotic systems have the following feature. So at early time, the OTOC is approximately given by the factorized value. But a signature of chaos is when the OTOC deviates significantly from its factorized value. So this is somewhere, this is basically the onset of chaos when the OTOC deviates significantly from the factorized value. And the scrambling time, T star, is defined as the time scale where the OTOC is significantly different from the factorized value, so somewhere here. So that's the definition of the scrambling time in terms of the OTOC. And actually, in chaotic system, the OTOC exhibits the Lyapunov behavior. So the deviation of the OTOC from the factorized value, that actually grows exponentially with time, as shown here. So this is very similar to what happens in classical chaos. So that's why this lambda L exponent, which is again theory dependent, is also known by the same name, the Lyapunov exponent. And this curly n, it's a measure of effective number of degrees of freedom per site. And as I said before, the scrambling time is defined as the time scale where the second quantity is order 1, so that the OTOC deviates significantly from the factorized value. So that gives us the statement that scrambling time is log of the number of degrees of freedom, which exactly how the scrambling time behaves. As I said before, this kind of OTOCs, they are notoriously complicated objects because both high energy and low energy degrees of freedom contribute to this kind of objects. So it was kind of remarkable that there is actually a universal bound on the rate of growth of the OTOC, thanks to Maldacena, Shenker, and Stanford. They basically showed that the rate of growth of the OTOC is bounded from above. So which translates into a bound on the Lyapunov exponent. So the Lyapunov exponent is always bounded by 2 pi over beta, where beta is inverse temperature. So conceptually, this is kind of remarkable because it tells us that quantum chaos cannot grow arbitrarily fast. So there is a universal bound on how fast quantum chaos can grow. And there is one more reason, there is another interesting reason why this is actually very important. So it is long believed that quantum gravity is maximally chaotic. So this chaos bound, which I'll refer to as the MSS bound, it gives us a definite meaning to the term maximally chaotic. So it's, by definition, it's the systems that saturates the MSS bound. And actually, this is in many holographic theories, you can actually check that this is actually true, that MSS bound is saturated. Even in SYK model, one can check that the MSS bound is saturated. So this is why the saturation is actually, or the MSS bound is actually rather important. In spite of all this progress, there are reasons to believe that this understanding of chaos is incomplete. For example, let's again look at the Lyapunov behavior of the OTOC. So the exponentially growing term, obviously, it's not bounded in the sense that it can grow it can be arbitrarily large. However, it's known that the OTOC is both analytic and bounded. So the left-hand side has to be bounded. That means this is only an approximate description. The OTOC must have other correction terms. Another way of saying it is basically this leading behavior, it's basically, if you have the full OTOC, this is just the leading term in the early time expansion of the OTOC. But the OTOC actually has infinitely many terms. This is just the leading term. But the MSS bound is a statement about this leading term. However, it is reasonable to believe that the other terms, other correction terms, they should be bounded as well. Because it's not that if you write down any expansion and you resum it, you'll get an analytic and bounded function. Analyticity together with the boundedness condition, it's a very restrictive condition, and it's actually requires that all the subleading terms, they should be highly fine-tuned. So it is not it is not impossible that there are other bounds on the subleading going terms as well. So the fact that the subleading the fact that we only have MSS bound and we don't have any bounds on the subleading growing terms, it's actually conceptually very unsatisfying, because the MSS bound is useful only for the leading term, but the leading term is basically a semi-classical effect. So all the other correction terms such as this, they are truly quantum mechanical. So since we are discussing quantum chaos, it would be really nice to actually have precise bounds on these quantum effects as well. And there is another kind of confusing aspect of this framework of chaos is basically there are hints from CFT that there can be an infinite set of new bounds beyond the MSS bound exist in quantum chaos. The reason is as follows. There are certain CFT regi correlators that can be thought of as special cases of the OTOC. And recently, it was shown that these CFT regi correlators obey an infinite set of constraints. But analogous constraints are missing in the chaos picture. So we don't know how to derive these CFT constraints directly from quantum chaos. So this suggests that we are possibly missing an infinite set of additional constraints beyond the MSS bound. So any question so far?
Sorry, I have a question.
Yes.
So can you explain maybe why how can you see that the first term is semi-classical and the second term is Kundu?
One way to one simple explanation is if you look at the maximally chaotic systems, the first term basically this term basically comes from just simple Einstein gravity effects. So all the other terms they come from either stringy effects or high derivative corrections, things like that. In that sense, the first term is the semi-classical term. Another reason why it's called a semi-classical term is exactly because it shows the Lyapunov behavior similar to the classical chaos. So it's kind of mimic the classical behavior. So that's why the leading term is generally believed to be a semi-classical term.
Also, Sandipan, is it clear that the rest of the terms are exponentials? They could be powers or different, right?
That's a very good point. No, this is just like something I wrote it down.
Okay.
So generally, like physically, it's kind of, there are reasons to believe that it's always like sum over Lyapunov behaviors. So that those kind of terms will be there, but they might not be the dominating terms. There can be like other terms, for example, there can be like some, so these kind of terms are also known to exist, like t times e to the power lambda t, things like that. So yeah, it's like generally these kind of terms will be there, but they might not be the most dominating subleading terms. Okay, any other question? Okay. So the goal of this talk is to address these questions by adopting the simplest possible approach that I could think of. I'm not going to do anything fancy. My goal is not to do that. So the goal is to start from basic properties of the OTOC that that are well understood, and then derive bounds systematically. So, for example, it is the OTOC is known to be analytic and bounded, as I said before, and the MSS bound follows directly from these properties. So we are not going to assume anything beyond the assumptions that are made in the derivation of the MSS bound. We are going to assume the same thing. But first, I'll argue that MSS bound actually does not utilize all these properties, does not fully utilize all these properties. So because of that, there are actually other bounds. And the goal is to derive these additional bounds systematically. So in essence, this is very similar to what we do in conformal bootstrap. And because of that, actually, some of the characters from conformal bootstrap will also show up here almost naturally. Another interesting thing that I'll focus on is basically quantum systems that are maximally chaotic. After all, maximal chaos provides a bridge between quantum chaos and quantum gravity. So the goal would be to learn general lessons about quantum gravity by studying some aspects of maximally chaotic quantum systems. For example, I'll argue that the MSS bound actually cannot be exactly saturated. What I mean is that even without any small duration of time, it does not matter however small, the MSS bound is only an approximate statement. So when you saturate the MSS bound by the leading term, there has to be other contributions for a, so those contributions can be small, but they have to be there. Otherwise, it will be inconsistent with the basic properties of the OTOC. So in other words, maximal chaos is an approximate idea. And as an application of the bounds that I'm going to derive, I'll show that these other contributions, they also satisfy some very precise universal bounds. More generally, what I'm interested in is basically how to analytically complete the maximally chaotic OTOC. So the way the MSS bound or the maximal chaos should be thought of is as follows. It is basically, if you expand the OTOC, the leading order term that saturates the MSS bound, and that's when we call the system to be maximally chaotic. But it's just the leading order term. So just like in effective field theory, even here, the leading order term should be analytically completed. So, and unfortunately, almost nothing is known about how to analytically complete the maximally chaotic OTOC. So this is something I'll also focus on. I'll try to address what are the analytic completions of maximal chaos. And the expectation is that this will be of importance in quantum gravity. So this is the outline of the rest of the talk. Let me pause for questions. Okay. So let's begin. So the first, let me discuss the relevant timescales for chaos. Consider any thermal quantum system with a large number of degrees of freedom and a simple Hamiltonian. Quantum chaos actually makes sense only when the system has a large number of degrees of freedom, so that we can discuss about small perturbations. So I'll mainly discuss three timescales. The dissipation timescale is the timescale above which the thermal 2-point function decays exponentially. And generally, the dissipation time is the order of beta. Then there is the scrambling time, which, as I said in the beginning, it is basically the time scale at which the OTOC deviates significantly from the factorized value. And since the scrambling time scales as log of n, so there is an parametric separation between the dissipation time scale and the scrambling time scale. So another important time scale is the factoration time, which is of interest in this talk. So this is basically the time scale above which the OTOC starts to decrease from its factorized value. So somewhere here, let's say. So it's basically starts to decrease from the factorized value, which is FD. And also above T0, all the time ordered correlators, they are approximately factorized. So in all systems with large number of degrees of freedom and simple Hamiltonians, the factoration time T0 is larger than the dissipation time, but they are not that different from each other. So parametrically, they are of the same order. So the scrambling time is always much, much larger than both dissipation time scale and the factoration time scale. And we are interested in times much, much larger than both the dissipation time and the factoration time. So that's where the chaotic dynamics dominates. So this is the time scale of interest for studying chaotic dynamics. One advantage of this region is basically for large time, all the transient effects, they decays exponentially, so we don't actually have to worry about the transient effects. We can just ignore them completely. So now let's discuss the basic properties of the OTOC, the things that we are going to utilize. So as I said before, operators V and W, they are simple local Hermitian operators. And just from definition, one can show that as a function of complex T, the OTOC is analytic in this half strip, where the real T is positive and the imaginary T is between beta over 4 and minus beta over 4. So in this half strip, the OTOC has to be analytic. Similarly, from the definition, one can show that the OTOC satisfies the source reflection condition, where the bar represents a complex conjugation. And finally, the OTOC satisfies a boundedness condition. So the OTOC, the absolute value of the OTOC is bounded by the factorized value FD, where the factorized value is defined over here for real T larger than the factoration time. So in the half strip, the OTOC is bounded by the factorized value when you are above the factoration time. So this is, roughly speaking, is a statement about unitarity, because in the derivation of this bound, you have to start with some positive norm and you have to use some kind of Cauchy-Schwarz inequality. So the positive norm is basically, in some sense, a statement of unitarity in this case. So this is, for any unitary system, this boundedness condition is expected to be true. So now we know that the OTOC is both analytic, bounded, and obeys Source reflection condition in this half strip above the factoration time. The MSS bound follows directly from these conditions. But I'm going to argue that from these three conditions, we can actually derive many more things. Actually, the main mathematical argument is rather straightforward. In my opinion, only non-trivial part of the argument is the realization that there are other bounds that follows from these conditions. So, in fact, once you realize that there are other bounds that follow from these conditions, one can derive these bounds rather easily. So, so to proceed, let me give you a rigorous argument why the MSS bound, why I believe that MSS bound does not capture these properties completely. So in the beginning, I gave you some hand-waving argument. Let me now give you a very precise statement that shows that there are more bounds. The starting point is this contour integral. So it's a contour integral in T prime, where the contour is shown here. So this is the contour. And if you look at the integrand, it's analytic everywhere other than this point over here, where you have a simple pole. So from there, you can evaluate this integral using the Cauchy formula. But actually, it is possible to evaluate this contour integral in a formal way. So if you do that, you can write down a dispersive sum rule for the OTOC. So we are looking at times much larger than the factoration time. And the right-hand side, I have an integral over t prime. So from the boundedness condition, one can easily see that this integrand is always positive, even though we may not know the exact value of the integrand, but it's always positive. So that's why it's a dispersion relation. So now when we know this dispersion relation, we can do a couple of things. First of all, we can construct any operator D such that when D acts on this function, it stays positive. So we can just construct any such function. And now if you go back to the dispersion relation, that means basically the same operator acting on the left-hand side should also be positive, because now you also have a dispersive sum rule for that quantity as well. So that means if I have such a D operator, then I always have a positivity condition like this. And it is actually very easy to construct such D operators. You can actually construct infinitely many independent D operators in this way. And because of that, basically, you can derive all these consistency relations. And physically, these are very similar to bootstrap equations that one have in conformal bootstrap. For example, if I start with this D operator, so this satisfies the first condition here. So we have this inequality, and this is exactly the MSS bound. So this is an alternative derivation of the MSS bound. But this is just a very simple choice for the D operator. One can choose D operator like many other D operators which are completely independent from this one. So that's why I said that the OTOC satisfies many more consistency conditions beyond the MSS bound. But this is actually, practically speaking, this is not actually a very good way to derive bounds on the OTOC, because now it depends on how cleverly one can choose this D operator. And that's not a very good way to derive optimal bounds. So since we now know that there are other bounds, what we can do is basically we can now perform a more systematic analysis. So that brings us to our second topic. So these new bounds on chaos. So now what I'm going to do is basically I'm going to define a new quantity, which is a moment of this OTOC. And in terms of that quantity, we can actually derive these constraints, and actually this constraint can be organized in a very systematic way using these moments. So this is the definition of the moment. So what we have, the OTOC over here, we have some kernel, and we have an integration along the imaginary t direction. So the real t is fixed, and we are integrating along the imaginary direction. And this j over here, you can think of that as spin. So this is a definition of a local moment of the OTOC. As I said before, this is in terms of this moment, all the bounds are actually very simple, and they can be organized systematically. Note that the right-hand side is analytic in the half strip. So using that, what we can do, so and this integral over here is basically exactly this integral. So using the analyticity property, what we can do, we can replace this vertical integration by these two horizontal integrations. And then using the source reflection condition, we can relate this integral with this integral. If you do that, you can write down a dispersion relation for the moment mu for any non-negative integer j. So j is 0, 1, 2. And as before, if we look at the integrand, it's a positive function because of the boundedness condition. So basically, we are utilizing all three conditions. So now we have a dispersive sum rule for the moment. Now, one might ask why I started with this particular kernel. Why not anything else? And there is a reason for that. So if you start with if you start with an arbitrary function over here, it's not that you'll be able to write down a dispersion relation for the associated moment. So only for a specific class of functions, you can derive dispersion relations, such as this. And this set of functions for non-negative integer j, they form a basis for those class of functions. So that's why this is a good choice for the kernel. Now, from this dispersive sum rule, we can write down precise bounds on the moments. First of all the moments for non-negative integer j, they are positive as well as bounded. So that's the first condition that one can derive. The second condition that one derive is the following. It's basically, as you increase the spin, the moment should decrease. Note one thing, in both these bounds, they cannot actually be saturated. So they are strict inequalities. That's actually very important. Then we can write down another non-linear constraint on the moments. It's basically the log convexity condition, which is this one. And this can actually be saturated. So this is the statement that as a function of integer j, moments must be a log convex function. Actually, you can derive some other bounds as well, but they are not as interesting. So I'll just stick to these three constraints. So before I proceed, any question? Okay. Now, what are some of the implications? First of all, again, let's start with a period of Lyapunov growth, which is this one. Then one can easily compute these moments. Computation of these moments are actually a very straightforward job. Like these are very simple integrals. So we can compute the moments exactly. Then if you play with this expression, you can convince yourself very easily that the only way both positivity and the monotonicity condition can be obeyed if the Lyapunov exponent obeys the MSS bound. So the MSS bound is contained in this infinite set of constraints. But note that for the derivation of the MSS bound, we don't even have to use the log convexity condition. So log convexity condition is something extra. Now let's look at the saturation, because it's of interest in quantum gravity. Now, if you saturate the MSS bound, then we can again compute the associated moments exactly. So the moments, only the spin 0 moment is non-zero, but all the other moments are exactly 0. But this is inconsistent with strict positivity condition. The positivity condition that I derived before, they are strict positivity conditions. So this is not consistent with those conditions. So this is the statement that MSS bound cannot be saturated exactly. So the OTOC must have other correction terms such that all the other moments get non-zero positive contributions. For example, let's add a correction term like this. So we have an overall 1/n term, then C1 and C2, they are order 1 numerical coefficients. And this is the second term is the subleading term. So we can ensure that this is a subleading term by introducing some small parameter epsilon. So this epsilon is small. So this parameter epsilon can be anything. It can be some higher powers of 1/n, or it can be some small coupling constant. So for the purpose of this discussion, the origin is not important. As long as epsilon is small, the second term is always subleading. Now, if I compute the associated moments, again, I can find it exactly. Now, again, if you use the positivity and the monotonicity condition, that actually gives you a precise bound on λ2, which is the coefficient of the subleading growing term. And it's basically bounded by 6 pi over beta. So note that the MSS bound is 2 pi over beta, but the bound on the subleading growing term is 6 pi over beta. And also the coefficient C2, there is a sign constraint on that coefficient as well. Naively, one might think that this is in contradiction with the MSS bound, but that's not actually true. It's true that the subleading term can grow faster than the leading growing term, but that does not mean that you can violate the MSS bound. So now one can further show from this chaos bound that this parameterization must break down before the second term can dominate over the first term. So that statement also follows from the chaos bounds, this new chaos bounds. So based in that's why even though the subleading growing terms can grow at a faster rate, but the overall OTOC can never grow faster than what is allowed by the MSS bound.
Sandipan, a question?
Yeah.
Is there a constraint? I would expect the coefficient C1 to be positive. Is that also true for C2?
Yes, the constraint this one. So it depends on the Lyapunov exponent λ2.
Okay.
So for example, if λ2 is between 2 pi over beta and 6 pi over beta, then C2 has to be negative.
Mm-hmm.
But if λ2 is less than 2 pi over beta, then C2 has to be positive.
Mm-hmm. So this second contribution can make the Otoc rise or decrease depending on the particular system. Okay.
Yeah.
Okay, thanks.
Now let's take one more step. What if I saturate even the subleading chaos bound? What if I saturate that as well? If I do that, then I get a bound on the next order Lyapunov coefficient. Now the bound is 10 pi over beta, and this constraint, this pattern actually persists even for higher order, even the higher order subleading terms. So far I'm just discussing about maximally chaotic systems. So you can actually also derive constraints when the leading term does not saturate the MSS bound. Even then, you can derive constraints on the subleading growing terms. But then there are some differences. If the leading term does not saturate the MSS bound, then you cannot actually constrain the Lyapunov exponent of the subleading growing term. But even then, you can actually constrain the coefficient in front of it. So I'm not going to actually discuss that at all. If you're interested, you can find them in my paper, or you can ask me later. You can actually derive strong constraints which are stronger than the MSS bound, even for non-maximally chaotic systems. So I have to admit that these new chaos bounds, I find them conceptually rather satisfying for the following reasons. First of all, the MSS bound is already contained in this new chaos bounds. Second of all, these new chaos bounds, they actually lead to constraint on the subleading growing terms, which are, as I said before, they are really quantum effects. And more importantly, I'm not going to discuss that here, but one can actually derive the infinite set of constraints on the CFT rigid correlator that you get from conformal bootstrap. You can actually derive those constraints directly from these new chaos bounds. So basically, this closes one of the loophole of finding out the CFT bootstrap constraints from chaos bounds. However, to be honest with you, it does not feel like we have a better understanding of chaos. For example, even though we have this infinite set of constraints, the physical meaning is still unclear. So, so let us pause and ask a couple of questions. So, for example, we should ask, what's the physical meaning of these new chaos bounds? So we have some formal statements, but the physical meaning should be more clear. Also, on a practical level, it is not very clear how to implement these bounds. So after all, we have an infinite set of constraints. So let's say you give me an OTOC. So do I have to check an infinite set of constraints to find out whether that OTOC is physical or not? That's on a practical level, that sounds like a nightmare. So this is basically related to the fact that these bounds, they are written in terms of the moments. So whenever I want to use them, I need to have some functional form for the OTOC. And that makes it really annoying, because even though we have general statements, the only way we can apply them is by just looking at special cases. Actually, these are related to some more conceptual questions. For example, even though these chaos bounds, they are completely non-perturbative, so far, the only way we are using them is by imagining that we have some kind of perturbative expansion of the OTOC. So even though we are starting with some non-perturbative bounds, we are imagining some perturbative expansion in terms of Lyapunov exponents, and then we are using our bounds. But it would be better to have a more non-perturbative understanding of this OTOC and also these chaos bounds, so that we don't actually have to expand around the leading term, or we don't actually have to expand in 1 over n, things like that. A related question is basically, how do we analytically complete maximal chaos? Even though we have some bounds on the subleading growing terms, still we have no clue how to analytically complete the leading maximally chaotic term. And these questions, these appear to be really hard questions. The reason is, in my opinion, the reason is we are not using the right language to discuss quantum chaos. So because of that, all these questions, they appear to be rather complicated. However, surprisingly, all these questions, they are actually related to a simpler question which can be solved exactly. It's the question of saturation of all these new chaos bounds. This is a question that I'm going to discuss next, and this is a very simple question that has a precise and unique answer. And that's important because, as I'm going to argue, that all these other questions, they are closely related to this question about saturation. So that leads us to the last part of our talk. Any question? Okay. So let me first explain what do I mean by extremal chaos, or more precisely, what's the difference between maximal chaos versus extremal chaos. So as I said before, maximal chaos is the statement about saturation of the MSS bound, and it gives you this particular OTOC. But as I said before, this is only an approximate statement, and the MSS bound is a statement about the leading order term. So this is an approximate idea, and obviously, as I said before, this OTOC should be analytically completed. In fact, if you look at this OTOC, beyond the scrambling time, this is not even bounded. So it violates the boundedness condition. So we know that at least around the scrambling time, there should be other large corrections, which make this OTOC both analytic and bounded within the half strip. So that's what I mean by analytic completion of the maximally chaotic OTOC. Now the extremal chaos is defined in the following way. So we have this new chaos bounds. And from this new chaos bounds, you can actually derive an infinite set of strict inequalities and an infinite set of inequalities that actually can be saturated. So the extremal chaos is defined as follows. We saturate all the inequalities that can actually be saturated without violating the strict inequalities. So that's a straightforward definition of extremal chaos. And surprisingly, if you do that, there is a unique solution. And that's the part that I found really surprising. If you just do the computation, I'm not going to show the mathematical argument, it's not very complicated. So if you do that, you'll find this OTOC. So this is completely fixed up to a new scale, which is the T effective, which I'll talk about that later. So it's an independent scale. It can be equal to the scrambling time. It's completely independent. It's completely arbitrary. So other than that, this OTOC is completely fixed. And as you can see, this is well behaved even after the scrambling time. In the early time limit, or if you expand in 1/n, the leading term is just the standard maximally chaotic OTOC. But this is basically an analytic extension of the maximally chaotic OTOC, which is obviously well behaved even after the scrambling time. And this is a pictorial representation. So this is the extremal OTOC. And this dashed line, this is basically the maximally chaotic OTOC, which this is the maximal one, which obviously agrees with the extremal one at early times, at times below the scrambling time. And T effective, it's basically the time scale at which the OTOC has the lowest value, or it has a minima. So in some sense, T effective is the effective scrambling time, because at that time scale, it's the time scale at which information is maximally scrambled. But after that, as you can see, the OTOC increases again, and it asymptotes to its initial value.
Sandipan, so I noticed that this extremal chaos does not have any of the terms Panos was asking about. These are terms that go like T to some power and then multiplied by the exponential. Mm-hmm. Is that a feature of the output of the computation, or is there an assumption that's built in?
No, this is an output. So okay. In the derivation, you don't actually have to assume the functional form. So if you saturate all the chaos bound in terms of moments, so that just gives you a unique solution.
Okay, thank you.
So yeah, so it does not have those kind of like polynomial times, exponential, those kind of terms are not here. If you saturate all these chaos bounds, those kind of terms will not be there. Okay, so some of the features of this extremal solution.
Can I ask something that depends on the previous? Is it clear that it always needs to return to FD? Unique solution in that, or there is some ambiguity?
No, it's a feature of the solution. Like it is, so there is no free parameter that I could introduce. It's basically like it's completely fixed.
Okay.
So, and because of that, as you can see, the extremal solution does not have any information loss. So because at very late times, it basically it saturates, it asymptotes to FD. So basically no information is lost. But then obviously one should ask, can a system be exactly maximally chaotic or exactly extremely chaotic? The answer is no, for the following reason. So if you look at the extremal solution, you'll see that it has singularities at points where the OTOC should be analytic. So that's why a physical system can never be exactly extremely chaotic. But these singularities can actually be, these singularities are very, very similar to singularities that we have in QFT, and they can be removed by the standard I epsilon prescription. So if you do that, you will get an OTOC which is which is nearly the same as the extremely chaotic OTOC, but there will be some small variation near T effective. Other than that, it's almost identical to the extremal OTOC. So a system can be approximately extremely chaotic, but it cannot be exactly extremely chaotic. In fact, this non-analyticity actually tells us something physical. This non-analyticity basically is telling us that the extremal OTOC should be interpreted as a distribution. So more precisely, what I mean is the following. So one can show rigorously that any OTOC can be represented as an integral of the extremal OTOC. So this F extremal is the extremal solution that I discussed times some function rho of T prime, and there is an integral over T prime. So this rho should be interpreted as a density function, because like this is almost identical to the Cullen-Lehman representation in QFT. So this rho has a natural interpretation as a density function, and that interpretation is actually even more. It can be made more rigorous by writing down an inversion formula for the density function. This is an exact inversion formula. So that one can derive using the dispersion relation that I discussed in the beginning. So if you look at the inversion formula, without knowing anything about the system, we see that this density function is strictly positive function, is a strictly positive function. So that's why this interpretation as a density function is an appropriate interpretation. In fact, from the inversion formula, we can say many more things about the density function. First of all, the density function should be real. It's, as I said, it's non-negative, and it's a smooth function. Plus, there is an upper bound on the density function. And the advantage of this representation is that all the chaos bounds are automatically satisfied. So in this representation, if the density function satisfies these four conditions, all the chaos bounds are automatically satisfied. You don't actually have to check whether we have an analytic function or not. Like, this is basically inbuilt in this representation.
Sandipan, can I ask something here, because I'm a bit confused? So usually when you do Cullen-Lehman, I think you go from position to momentum space, right, to energy space when you have spectral representation. Here, both functions are functions of time.
Exactly. Yeah. So this is not exactly like, it's basically an analog. So here we have an integral over time, not energy. Right. So when I say it's very similar to Cullen-Lehman type representation, it's just an analogy. Like, it has similar features and everything, but like, it's obviously, like, physically this is completely different.
So do you understand what this density function is? Because it's a density in time, the physical meaning, or?
I can give you a couple of examples which can make things easier to understand. So how much time do I have? So I started a little late, but I'm not sure how much time I have.
Yeah, we started like 10 minutes late, so we can go a couple of minutes over time, I suppose.
I think 10 minutes is fine. Okay. So let me give you a couple of examples, and actually, to be honest with you, in my opinion, I think this is the right language for talking about quantum chaos, because everything that we know about, all the rigorous statement about quantum, about the OTOCs that we know about, they are automatically inbuilt in this language. And one more thing, the OTOC, like the left-hand side, that OTOC doesn't even have to be a maximally chaotic OTOC. Like, this is true even when the OTOC does not have any a region where it saturates the MSS bound. This is true in general. For example, when you don't saturate the MSS bound, so when lambda1 is less than 2 pi over beta, using the inversion formula, you can actually compute the density function exactly, and it has the following feature. So this is the density function. So it decays exponentially, and this dashed line is basically the bound it's basically this bound. So around the scrambling time, you can see that the density function actually is inconsistent with the upper bound on rho, and that means basically, obviously, there has to be correction terms, which actually makes the density function smaller than this value. One really interesting example is basically the extremal chaos. Extremal chaos is basically a single particle state where the density function is a delta function. And obviously, this is in tension with the boundedness property. But this is a manifestation of the fact that the extremal solution is non-analytic. So because of that, that's why we can have a delta function because it's not completely physical. So in physical systems, what you have to do, you have to replace the delta function by a narrow distribution, so that it's consistent with the boundedness condition of rho. So that leads us to the idea of small deformation of extremal chaos. So you can replace the delta function by some narrow distribution, which is defined as follows. The integral of the density function is basically dominated by a very small window around some T effective. So as long as delta T effective, which is the width of the window, is much smaller than T effective, that's basically a small deformation. Is basically you are just replacing the delta function by a distribution which is narrow. To give you a couple of examples, you can just replace the density function by other functions, such as this, where you preserve the area, but you are just smoothing out the delta function. This is important for the following reason. Now let's consider maximal chaos. So we have, let's say in a system we have a period of maximal chaos up to some time scale which is close to the scrambling time. We can compute the corresponding density function, and basically the density function is approximately zero. If you start with the exact maximally chaotic OTOC, then it's exactly zero. But obviously, since we know there has to be corrections, and those corrections are small, so the density function is approximately zero, at least up to the point where the maximally chaotic OTOC is a good approximation. So let's say somewhere up to here. Now, since we have a period of maximal chaos close to the scrambling time, so basically that means this time is around scrambling time, but obviously it can be a little bit smaller than the scrambling time. On the other hand, above the scrambling time, we know from the boundedness condition, which is basically the boundedness condition is a statement that the density function is bounded by an exponentially small function above the scrambling time. So we know that above the scrambling time, the density function should also be very small because it's bounded by an exponentially small function. So the density function can actually be significantly large only within a very small window, somewhere here. Actually, this is not. So something like this. And the center of the midpoint of the window, which is basically T effective, cannot be much different from T star. And delta T effective is basically obviously much smaller than T star. So this is the definition of small deformations of extremal chaos. So without knowing anything about the details of the system, we can say that all analytic completions of maximal chaos are small deformations of extremal chaos. So that's why this language in terms of the density function, I think, is the right language, because in terms of this language, all the analytic completions of maximal chaos are small deformations of extremal chaos. However, you should always remember that the actual OTOC can differ significantly from the extremal OTOC. Even though the actual OTOC differs significantly from the extremal OTOC, when we discuss in terms of the density function, it's always a small deformation. That's the important aspect of this representation. As an example, one can just check the Surgeon theory, which is basically jetty gravity. For jetty gravity, one can compute the OTOC as an expansion in 1 over n, and you have an exact result which is valid even above the scrambling time. And from that result, you can actually compute the density function. And it's basically a small deformation of extremal chaos, where the mean is around the scrambling time and the width is some order 1 number times beta. So the width is much small compared to the position of the peak. Same thing can be checked for 2D safeties with large central charge. The density function has very similar features. So these are like 2 examples as a verification that whatever we said about analytic completions of maximal chaos, they are consistent with known results. So at this point, I can make a very conservative conjecture that all theories of quantum gravity and their holographic duals are strongly chaotic systems that are small deformation of extremely chaotic systems. This is a very conservative statement, which follows from the first scrambling conjecture anyway. Any question before I go to the last slide? Okay. The last thing that I want to mention is basically a very amusing observation that I think can be of importance, but it can just be a coincidence. So if you just take the spectral representation and replace T prime by energy, T by chemical potential, and beta by 2 pi Boltzmann constant times T. So now we end up with, in these new variables, we end up with some integral over energy. Now, if you look at this quantity, is basically some version the extremal solution and 1 minus extremal solution. It's exactly the Fermi-Dirac distribution. So somehow from our analysis, the Fermi-Dirac distribution is emerging naturally. It is possible that this is just a coincidence. There is no deeper meaning in this identification, but anyway, this is kind of really amusing to me. Even though this can be a coincidence, this has some application. Because of this identification, what we can do, we can actually use mathematical tools available for the Fermi gas to actually analyze quantum chaos. For example, it is possible to actually derive very general results about small deformations of extremal chaos by using some of the known results from Fermi gas. If you are interested, you can look into my paper or you can ask me later, but I'm not going to discuss that here. With that, let me conclude. First of all, I hope I convinced you that a lot can be learned about quantum chaos directly from basic principles. The OTOC must obey an infinite set of constraints in any thermal quantum system with a large number of degrees of freedom. So this infinite set of chaos bounds include the MSS bound as the leading constraint, but this infinite set of bounds also constrain the subleading going terms as well. Surprisingly, there exists an extremal OTOC, which is a unique analytic extension of the maximally chaotic OTOC, saturating all the chaos bounds. The extremal OTOC provides a Kellen-Lehman type representation for all OTOCs. And in my opinion, this is the right language for studying quantum chaos, especially maximally chaotic systems. Finally, I argued that all analytic completions of maximal chaos are small deformations of extremal chaos. So extremal chaos should be of importance in quantum gravity. With that, let me finish. Thank you for your time.
Okay, let's thank Sandipan for a great talk. Do you have any questions? Okay, I have a question. for the Schwarzian case, for instance, you showed the plot, right, of the Otoc, and it has the familiar behavior that starts from the factorized value, and then it decreases and it plateaus to some constant value. And the way, at least I understand it, is that the correlations that you had at the early times are in some way lost by the chaotic nature of the system.
Yeah.
Why I'm confused when I see the other plots of the extremal chaos or the small perturbations of extremal chaos, because I don't really have any intuition of how to think about the slope where the Otoc starts going up again. How do you have an intuition of how should we think about that?
Why you mean like why the OTOC starts to increase after some point?
Yes, exactly.
I actually, to be honest with you, I actually don't understand it completely. So, so in some sense, it feels like the extremal solution is some kind of like an integrable system or something like that. It's not actually chaotic. It looks to be chaotic for some period of time. So that's my understanding of the extremal solution. But I don't really know, because if I could find some example where there is an OTOC which behaves almost like that, from there I could learn something. But I don't know of any example even similar to that. So this is something that I'm thinking from various other perspectives as well. For example, from ETH, things like that. But like still, I don't have a very concrete answer. And actually, this can actually be kind of important. For example, like all the known examples of quantum gravity, such as like Schwarzian theory, things like that, there is always the information problem, because at very late time, the OTOC always goes to 0. And on the other hand, the extremal solution has the other problem. So it doesn't go to 0, it goes to its initial value. So somehow like this might have something to do with the information loss problem. But
right, is this just the unitarity, right? If you have a unitary system, in the end, it should go up again, right? That's the.
But like it should not go back to its initial value. Like
yeah, exactly. That's why I asked.
I guess that a combination of both these effects can be of like importance, I guess.
I see. Thank you. Any other questions?
Yeah, I have a question. So this isn't specific to your talk, but it's just a general question about quantum chaos, because I don't know much about it. So, my intuition about chaos is the classical intuition, where you have a system that starts off with two slightly different trajectories, but after a long time, they diverge by a lot.
Like
you had at the end of your talk. But for this quantum description of chaos in terms of the out-of-time ordered correlator, there is some inherent thermality that comes into play. And I don't understand why any discussion about chaos, what it has to do with thermality. Why does thermality come into play? This doesn't seem to be the case in the classical case. There was no mention of temperature or anything like that.
Yeah, that's a very good question. Actually, so in some sense, there is classical chaos and quantum chaos. They are similar, physically similar, but they are actually distinct objects. So as you said, in classical physics, in classical chaos, actually you don't need temperature to have butterfly effect. But in quantum systems, all known chaotic systems, the only way you can measure chaos is by attaching that to a thermal bath. Or there should be some notion of temperature that should be present to have a chaotic system, quantum mechanically chaotic system. So that's the feature of quantum chaos. So in some sense, that's why it's quantum chaos is distinct. So actually, there are some recent works where people are trying to start with systems where initially you don't have a temperature, then basically you make some perturbation and you end up with some like thermostat at the end, and then study chaos in that system, things like that. But they are like very preliminary studies. So like, to be honest with you, not much is known about quantum chaos. It's a very complicated subject.
Okay, thank you. And also a very nice talk. Thank you.
Any other questions? Okay, let's thank Sandipan again for a great talk.
Thanks for the invitation.